Conformations are also important for cyclic molecules. In this lesson, we will consider the cases of 3, 4, and 5-membered rings, and then in the subsequent lessons, we'll handle the more complicated but important case of 6-membered rings. So once molecules are forming rings, what we have to be thinking about most is the angle that is required for a certain ring size relative to the desired hydrogen-carbon-hydrogen or carbon-carbon-carbon angle of 109.5 degrees. So as we're going to see, for a number of ring sizes, there is an energetic cost that has to be paid to have that ring size. And the term we use for that energetic cost is called angle strain. The greater the ring causes the angle to deviate from its ideal value of 109.5 degrees, the greater the angle strain. Okay, so let's review a little bit of geometry and look at the interior angle size of various different polygons. A triangle, which we could approximate for a 3-membered ring, has an equilateral triangle at least, has an interior angle of 60 degrees. A square has an interior angle of 90 degrees. A pentagon has an interior angle of 108. A hexagon is 120. A heptagon is 129. And an octagon is 135. Okay, so looking at 3-membered rings first, as you could probably imagine, that 60-degree bond angle makes 3-membered rings really unhappy. 60 is far from 109.5 degrees. Therefore, cyclopropane is destabilized by 112 kilojoules per mole. Ouch! Relative to linear propane. How do we know this? We measure what's called a heat of combustion. Okay, so combustion is a chemical reaction in which you take a hydrocarbon and heat it up, burn it in the presence of oxygen, and it gets converted into carbon dioxide and water. Okay, this is fundamentally what happens when you burn oil for heat or gas for heat. So carbon dioxide and water are low energy products of this reaction, so the combustion reaction is going to have a negative delta H and delta G of reaction. So the way this helps us is if we measure the heat of combustion when we combust linear propane versus the heat of combustion when we combust cyclopropane, we find out that the heat of combustion is greater for cyclopropane. And that's going to make sense because cyclopropane is a less stable starting material. It has further downhill to go to get to the stable combustion products. Okay, but angle strain is not the end of the story. For a 3-membered ring, not only is there angle strain, but there is also torsional strain because all of the CH bonds are eclipsed. Okay, so looking at the model of cyclopropane, if you look down one side of the triangle, you see a CH bond and another CH bond on the adjacent carbon, and those bonds are eclipsed. Look down another side, the bonds are eclipsed. The third side, the bonds are eclipsed. And there's nothing we can do about that. We can't wiggle this structure in any way to relieve the eclipsing of the bonds. Okay, so the combination of angle strain and torsional strain, which is present in a cyclopropane, is what causes the destabilization of 112 kilojoules per mole. The fact that you can make cyclopropane with your model kit, but it looks really distorted. You can see that these sides are not straight, and it almost looks like the model kit wants to break. That is representative of the strain associated with this molecule. If I open up the 3-membered ring, it's going to relieve a lot of the strain, and if I try to reform the 3-membered ring with my model kit, I have to try really hard to put this together carefully so as not to break the model. Okay, in the case of 4-membered rings, the angle strain is not nearly as severe because the interior angles of a square are 90 degrees, and 90 degrees is much closer to 109.5 degrees than 60 degrees is. Okay, so here's a model of a four-membered ring if it were planar. However, there is even more torsional strain in a planar conformation for four-membered rings than there would be in a three-membered ring. Because in a three-membered ring, there are 6 eclipsed carbon-hydrogen bonds. In a four-membered ring, because there are 8 hydrogens, there are 8 eclipsed carbon-hydrogen bonds. Now, if you take your model and play with it a little bit, with the three-membered ring, we saw that everything had to be completely planar and there were no degrees of freedom. It has to stay in a plane. With a four-membered ring, the molecule can dance around a little bit. Okay, it does not have to lie strictly in a plane. We could take 2 of the carbons and bend them down a little bit, and 2 of the carbons and bend them up a little bit. So now the question is this better off or worse off? Well, this conformation is what we call the puckered confirmation, and it turns out that this relieves some of the torsional strain. If you look down a carbon-carbon bond, these 2 CH bonds are no longer strictly eclipsed. They're not staggered, we haven't gained that much, but they are not completely eclipsed, they're a little offset from each other. So that relieves some, but not all, of the torsional strain. Again, I could look down any set of carbon-carbon bonds and see that the CH bonds coming off of them are not completely eclipsed in the puckered conformation. We pay a slight energetic price in terms of angle strain. This causes the angles to compress to 88 degrees instead of 90 degrees. But that's still lower in energy overall than the planar conformation because of the reduction of some of the torsional strain. Okay, what about five-membered rings? Well, this should seem simple. There should be minimal angle strain because the interior angle of a pentagon is 108 degrees, and that is very close to the 109.5 degrees that's the ideal tetrahedral angle. In fact, these angles are close enough that for all intents and purposes, we say that there is no angle strain associated with a cyclopentane. However, there is torsional strain, right? Because if you look down any of the 5 carbon-carbon bonds, you see that in a planar conformation, the CH bonds are completely eclipsing each other. And that's not good news because now we have 10 hydrogens, which means that there are 10 CH bonds to eclipse each other. So the planar conformation has more torsional strain for the 5-membered ring than it did for the 4-membered ring. So what did the 4-membered ring do? It played around a little bit to relieve some of its torsional strain, and the 5-membered ring can do that also. The 5-membered ring adopts what's called the envelope conformation. It's called that because one corner bends up like the flap of an envelope. Okay, so if you look at this model, and I strongly encourage you to get out your model kit and make a model of this yourself and play with it, you can see that this carbon is flipped up relative to the plane defined by the other 4 carbons. Again, this increases angle strain a little bit, but it relieves some of the torsional strain. Why? If we look down a carbon-carbon bond that contains the flap of the envelope, that looks almost staggered. Not quite staggered, but almost staggered. Same thing for this carbon-carbon bond. And even the carbon-carbon bonds that are the sides of the envelope, if you look at them carefully, they are also going to be somewhat staggered. The only carbon-carbon bonds for which the CH bonds are completely eclipsed is the bottom of the envelope, the side furthest from the flap. Okay, so we can relieve 4/5 of the torsional strain associated with this molecule. Yes, you introduce a little bit of angle strain, but once again, this conformation is lower in energy overall than the planar conformation is.